Good afternoon. So I'm Vijay Karki from LSU. So today I'm going to talk about computer simulation and visualization studies of disorder and defective system. I'll not uh, present a lot of results. I just talk about the simulation and visualization aspect. So for me, these disorder and defective systems are these. I mean, of course, there are others. So disorders, so liquids and gases. So we have studied quite a lot liquids. For example, we have covered the MgU SiO2 joint and also simulated diapside, anorthite, and then some hydrous metals, hydrous silica and hydrous silicate. So we particularly looking at equation of state, thermodynamics, structural properties, dynamical properties like diffusion coefficient and viscosity. And for defective system, we look at mainly so far point defects, so native defects like vacancies or interstitial atoms, and then also impurities, only protons so far, and look at these four minerals. And we also plan to do extended defects and did a little bit work in MgO. For example, we have recently simulated single tilt boundary in MgO and look at vacancy formations in the interface regime. So basically looking at atomic electronic structures and defect energetics, means defect formation as well as migration energies. So all these results are certainly important for better understanding of geophysics and geochemistry of the planet. Okay, so computational approach has been very popular in this area for last 10, 15 years. And the major advantage are like for the accurate prediction of several key properties, and at the same time, it will also help us to reveal underlying microscopic mechanisms at a atomic or electron level. And then the recent advances in both hardware and software enable basically to deal with all sorts of problems, very intensive computational and data-wise. And then another advantage is, so it has basically established a link between theory and experiment. So in fact, it is a complementary approach. So there are two ways two or three ways it is helping experiment. For one is like providing results where experiments or data are not available or difficult to achieve, and the other is to validate and maybe also guide future experiments. So computational study is certainly important, but there are a lot of challenges associated with this. And then because of these challenges, I think I can still say that computational study of earth materials is in very beginning stage. So the first thing is accuracy. So one important issue is always like empirical versus first principle physical models. So empirical based on experimental results. So you just have a parametric model by fitting available experimental data, whereas first principle physical models are defined in terms of atoms and electrons. Of course, there are also different levels. So we widely use DFT within LDA or GGA. And of course, for some application, you need a UTOM, and then maybe even going beyond DFT. And other issues are in terms of simulation, for example, large supercells. So most of the crystalline properties you can study with use of primitive cells and exploit full crystal symmetry. But once you go for defective system, like even if it has a single point defects like vacancies, or go for amorphous materials like glasses or liquids, there is symmetry breakdown or even completely absent. So we cannot exploit primitive cells. We normally need large supercells, and how large all depends on the type of the problem. For example, if you're doing a defect and if you're looking at isolated defect, then certainly you need a very, very large. Otherwise, there will be defect-defect interactions. And then another issue is you really need to make a very long simulations. Okay. Those could be simply related with structural relaxations, simply too many free parameters, or if you are doing MD simulation, by nature it will be a long simulation. You have to run for several steps. So So even if you decide with a particular supercell and then certain long, duration, but one simulation is not enough. You normally need to make a many simulation in order to completely solve the given problem. And at the end, whatever results your simulation will produce, so those results you have to analyze. In many cases, may be straightforward, some cases may not. So you need some sophisticated tools like visualization tool or so. Okay, so I have mainly worked with a first principle approach, although I have done also pure potential MD in some cases. So, so here I put in the context of molecular dynamics within first principle. So basically solving Newton's equation of motion. So you need interatomic forces, which can come from pure potential, but here it comes from first principle within the density functional theory. So basically treating atoms and electrons explicitly, and so we use the BAS PWS packages. So these are parallel codes. So I don't want to go in detail. So you already know about this. So let me show very important results. So this is all implemented in parallel environment. So you're doing basically parallel computing with Photon implemented with MPI. And so I have shown here some scaling using up to 250 processor for up to 2048 atoms. So you can see from here that depending upon size of the supercell, there is no need to use beyond certain number of processors. You don't gain anything. For example, if it is 64, even like going, I think this probably number of processor also 64, there is no point of going beyond that, at least for this pass for liquid with a certain choice of computational parameters. It can vary a little bit depending upon what system and what parameters you choose. So maybe for this one, 16 processor or 20 processor enough. If you go for 2000 atom supercell, maybe about 150 processor is enough. Okay, after that you don't get any improvement. So I did this test in one of the Linux clusters at LSU. So we do have quite a lot number of processors, so multiple machines under LSU HPC, and there is a Loney, Louisiana Optical Network Initiative, statewide initiatives, altogether probably about 10,000 processors, and half of them, or maybe 1/3 of them, are dedicated to just LSU. Other are available statewide and even outside the state. So I'll try to explain this, some significance of this later too. Okay, so large supercell. So normally we do using around 100 atoms or more. Okay, so certainly finite size effects are important. So that means when you use 100 atoms, if that size is not enough, then you have to do some corrections. Sometimes corrections are straightforward, like if you are doing calculating just the energy, maybe okay. But if you are doing some structure or so, you may not be picking up all the structural features. So in that case, you need largers. So for example, in case of amorphous materials like liquid and glasses, they do so this short and medium range order, and which could be easily 10 angstrom or so. So in order to capture that, you might need to go beyond 100 atoms supercell. The other problem which requires large supercell is multi-component materials. So we know that real samples, natural samples, are multi-component and with many components at very small concentration. So in order to represent all those concentrations, you need really large supercell. So for example, even for model basalt with a 244 atom supercell, so you can have these 4 different compositions. So for example, magnesium is only 14. Okay, so 14 magnesium is whether enough or not if you want to calculate magnesium diffusion, self-diffusion coefficients. So this is a kind of a small bound for me. Of course, I'll try to use a bigger, but all depends whether it can be used. Similarly, all defect bearing materials requires supercells, as I said earlier, isolated defects. So, and because normally those defects are at a very, very low concentration. Okay, so you have to take into account the defect concentration, otherwise it will, the calculation will be equivalent to a system at a high concentration. And then if you try to simulate dislocation or grain boundary, which are by nature extended defects, So linear or planar. So in order to represent them, you need really large supercells. So there is actually no limit on how large the supercell can be. So just showing for liquid, so MgSiO3, so this is before, crystalline, then melt. So this is just a rotated view, and you use a periodic boundary condition, so it is equivalent to a bulk system. This is for, I think, probably not only input, it's so for MgO till grain boundaries at different pressures, so symmetric, later boundary collapses, and then boundary becomes asymmetric. So you can see the one side move relative to other side. So these are already like a simulation involving around 500 atoms or so. Another aspect is, so you have to do very long simulation. So even if you are doing just a static calculation, because of defects or like let's say if you are doing glass or so, then you have more free position or internal parameters, so you have to relax all those. So for example, MgO, a perfect crystal, no free parameter. Once you have defect, then there are free parameters introduced. If you are searching for migration path and using NEB method, then you have to try several intermediate configuration and compute the energy and forces. So just because of this reduced symmetry and increased free parameters, you have to do longer structural relaxation. But if you are doing molecular dynamics, just in order to have an accurate representative ensembles, you have to do very long simulations. And if you are interested in dynamical properties, then even longer. So for example, with a typical time step of 1 femtosecond, if you do just 1,000, you cover 1 picosecond, but for some dynamical properties like a viscosity, you might need to go over nanoseconds. In that case, about a million steps. I have actually completed 1 or 2 cases, 1 nanosecond long runs. And then for glass age, the quenching rate, like how fast you quench the liquid to get the glassy state. And then if you are trying to do study pressure effect, so compression and decompression, at what rate you do. So all those things actually matter. So if you take care of all these, then you need to make a really long simulations. Yeah, this is just to show that in case of magnesium, so perfect crystal, no free parameters. Once you have defects, then essentially all the atoms see some level of displacement. That means they go under relaxation. Okay, so this is mean square displacement used to compute self-diffusion coefficient. So basically a square of displacement plotted as a function of time in all logarithmic scale. So you can see that in order to reach a diffusion regime where mean square displacement is directly proportional to time, you have at some condition you have to run really long simulation. For example, these green curves, hydrogen, everything is very fast, but for silicon and oxygen, you can see very slow increase. I'll have another 12 here. Okay, so this is for the previous one for hydrosilica. So dynamics is relatively fast, but this is a pure silica dynamics, very, very slow. I have already completed 1 nanosecond. Still, you start to see some linear regime, but since it is towards the end of simulation, you are still not sure. So even though you want to use 1 nanosecond, maybe you have to run for 2 nanoseconds so that this region becomes converged. And then only you can use this MST value to compute self-diffusion coefficient. So similarly for viscosity, so you need to look at autocorrelation functions. So here I plotted normalized one, otherwise there are initial values. So how fast those autocorrelation functions will make, how fast this computes coefficient, viscosity, where you have the integrand, how fast that converges. So again, at some condition you need to really long. So for example, in silica, I'm still not happy with the results, so trying to make a longer run for silica liquid at low temperature, relatively low temperature. Okay, so you decide to make a a large simulation, long simulation, and such simulation you have to make many. So one is to cover